Okay, let's learn all about logarithms, okay? I know logarithms sound complicated and intimidating, but they're really fairly straightforward, and I'll help you understand them as we work through this, okay? So, if x is positive and b is a positive constant not equal to 1, then y equals the log base b of x if and only if b to the y equals x. So, here's the deal. What part of this exponential equation is the logarithm equal to? It's equal to the exponent. So if you can remember that logs are exponents, that will really help you work with them. Also, a logarithm is the inverse of an exponential function. Okay? So in other words, if we take the exponential function here, and we switch x and y and solve for y, we end up with a logarithm. Let's see how this works. So let's convert this exponential equation to a logarithmic one. Okay, so we're going to say that the log of 8 base 2 is 3 because 2 to the third equals 8. Now let's go from a logarithm to an exponential equation. So y equals the log base 2 of x in exponential form is 2 to the y equals x. There's your base, there's your exponent, and that's what it's all equal to. So here's the definition of exponential forms of equations in logarithmic forms, okay? So if I'm starting out with y equals the log base b of x, I can rewrite that in exponential form as b raised to the y power equals x. If I have the logarithmic form of b raised to y equals x, in logarithmic form, that's y equals log base b of x. Knowing that, let's rewrite this logarithmic equation in exponential form. So there's our base, there's our exponent, and that's what it's all equal to. 10 to the second power equals x plus 5. And going in the other direction, let's write this in exponential form. Oh, same direction, right? We're going to do it with a different terms here. So b to the fifth equals all that. So b to the fifth equals b to the fifth. How about that? So that brings up an interesting little rule. If I have a log, let's say, where the base matches this raised to the x power, that's just going to equal whatever the exponent is. So as long as these two numbers match right there, then your answer is that exponent. Now let's write an exponential equation in logarithmic form. So the log of x base 5 equals the exponent 3. And let's do this one. The log of our base x of this number equals the exponent, which in this case is log of base x7. Well, that's a true statement, isn't it? So here's another little rule. If I have x raised to the log of the same base of anything, let's say b, that's equal to b. So as long as this term and that base year log match, and this logarithm is in the exponent, then the whole thing equals that term right there. So here are some really useful properties. The log of base b of b equals 1 because really when you think about it, this b right here has an exponent of 1. So that's equal to 1. Okay, the log of 1 of any base is always 0. Why? Because anything raised to the 0 power is 1. And we've already talked about this one, okay? Remember, if the base year log and the base of that little term inside the log are the same, then it's equal to the exponent. And finally, if this number and the base of the log match, the whole thing is equal to what you're taking the log of. So these are super useful properties that you want to memorize because you're going to use them over and over again. Let's apply them to these examples and you can see how helpful they are. So remember that the log of 1 of any base is 0. Remember what happens when we have the log base 5 of 5. If these numbers match, it's equal to 1. And finally, the log base 2 of 2 to the fourth. If these numbers match, it's equal to that exponent. So this whole thing is equal to 4. Okay, so let's talk about the graphs of logarithmic functions. Remember that logarithms are inverses of exponentials. So this is the graph of y equals 2 to the x. And 2 raised to the negative 2 power is 1/4. 2 raised to the 0 power is 1. 2 raised to the first power, 2 raised to the second power is 4. And so on and so on. 2 raised to the third power is 8, and 2 raised to the fourth power is 16. Now remember that if I have a function and I want to graph its inverse, all I need to do is switch the x and y coordinates. So if I want to graph the y equals the log of x base 2, that's the inverse of 2 to the x. And here it is. So instead of having a point on the exponential at negative 2 1/4, now on the log it's 1/4, negative 2. Instead of having a point at 2, 4, because 2 squared equals 4, the log of 4 is 2. And on the exponential, where we have 0, 1, on the logarithm, that's at 1, 0. And here with the graph of y equals x going right through the middle of them, you can see that, like all inverse functions, they are symmetric with respect to that line. In other words, they're reflections on that line. And finally, we're going to define a couple of logarithms that we use all the time. If I have a log of base b, it's called a common logarithm. And if I have a log of base e, it's called a natural logarithm. And we use it so much that it has its own little symbol, ln of x. And your calculator even has a special button for common logs. It's right here. And there's a button for natural logs. Okay, so if I do the log of 10, then we should get 1, because the log of 10 base 10 is 1. And if I do the natural log of e to the, let's say e to the 5th, whoop, there we go. Natural log of e to the 5th should be 5, because it's base e. There it is. Okay, so whenever you see the word common log, that means log base 10. And whenever you see ln of x, that means log of base e.